Welcome physics students, Mr. Steinerson here. In this video, I want to take you through the basics of free fall motion, which is basically a uniform accelerated motion. And we're going to get there by reviewing some of our other kinematic equations first. So grab your notebook, we're going to talk about free fall and also review our basics with kinematics. As we take a look at motion equations, our central question should always be, is it accelerating or not? So we can answer a lot of the same questions like, how far have I gone? Or what distance or displacement is the object travel? But we also have to ask ourselves, is it happening during acceleration or not? Notice how the velocity is constant in this example. Therefore, over those 10 seconds, it is not changing from 80 meters per second. Then we can assume that it's a constant velocity, and we can use our constant velocity equation. Solving for d will then allow me to answer this question. Plugging in 80 meters per second for 10 seconds, I get 800 meters. Of course, I'm using that average velocity to help me figure this out, but that is the big idea in this example. Now, why I'm going back to these basics is because you can also solve this by thinking about the area. Remember, in a velocity time graph like we have here, if we find the area under the curve, that will tell us the displacement or the distance. So if I take this shaded area and if I multiply the 10, which is the 10 seconds, times the 80, which is the 80 meters per second, I still get the same answer because that is what we're solving for, right? That quantity of displacement. We're going to take this idea and apply it to not just constant velocity, but also accelerated motion. So students, as you can see in this example, the velocity starts at a low number and over time increases at a constant rate. We have uniform acceleration. So if I'm looking at this as my equation, I need to remember I'm using the average velocity in order to solve for this. Therefore, once I put the values in, I'm going to get a value for the average velocity, which is the final plus the initial divided by 2, all right, times the time. Not just the velocity in the beginning, not just the velocity at the end, but I have to use that average velocity to give me the value I want. Now, plugging this in, of course, we get an average velocity of 50 meters per second. That times my time of 8 gives me my distance traveled of 400 meters. Now, this is the big idea between acceleration and constant velocity. We have to make sure that we're using the right equation for the right scenario. This equation that I've highlighted right here will work best when we have a accelerated motion. As you can see here, we start at a low velocity, we end at a high one. As you approach these problems, I really want you to always go back to the basics and ask yourself, are we accelerating uniformly or moving at a constant velocity? Notice in the first line, it says that this is a uniform acceleration. Therefore, we can use our uniformly accelerated equations in order to find out our distance. So I'm going to use the 1/2 VF plus VI times T. Noticing that I have a change in velocity, my final is 30, my initial is 0, and I know the time is 5 seconds. I can now plug those values in and solve for my final answer. Okay, now it's always important to start from the beginning and ask yourself that question, are we accelerating or not? And then go on from there. There might be times where the problem doesn't give you all of the variables that you need, and we can substitute what we know into the equation to help us create new kinematic equations. And that's what this is showing us right here. So if I don't know the final velocity, I can solve for final velocity, knowing that that's equal to the initial plus the acceleration times time. I then can substitute that in where I see final velocity. We can clean this up a little bit because I'm noticing now that there's a VI plus another VI, and an a times a t. Okay, I can clean those terms up algebraically by multiplying the vi's together and then still adding the a times the t. That's 2vi plus at times t. And lastly, I can even clean it up more by multiplying the t's together for t squared, and I can distribute that half. So now I end up with a term that doesn't have, or an equation, sorry, that doesn't have the final velocity term. This is another one of our kinematic equations, quick derivation. Once again, going back to the basics, if it's accelerating, we can use this equation. So I'm going to look for those words, and sure enough, it says accelerating in the problem. Now I can plug the values in. I know the acceleration rate is 4.8 meters per second squared. The time is 15 seconds. And I want to know the displacement, or the distance that will have to travel for that runway. So then I can plug my numbers in, and I can solve out, remembering to do your order of operations, and I get about 540 meters for this one. Check your work, and we'll move on to the next. We do have one more kinematic equation that is often used if we don't have the time. So now if you look carefully, we have the other variables, but time is an unknown. So we can use this equation where we take final velocity squared equals the initial velocity squared plus 2 times AD to solve for any of the givens or any of the unknowns in this equation. Okay, one more recap because it's that important. If you know if the velocity is constant, you can use this equation here. Velocity is distance over time, okay? However, if the velocity is changing, you need to factor in the acceleration, which is a change in velocity over time, using the average velocity over that interval. And that's true for all the uniform equations. So the only time we can use this equation is when we have a uniform velocity, when the velocity doesn't change. We're going to call that a constant velocity. This chart gives us a quick overview of all the equations that we can use for accelerated motion. So keep in mind that this is only for motion that is accelerated uniformly, all right? Now, what I'm also showing you in this chart is some equations have missing variables. Remember this last one we just talked about? We can solve for a problem that does not give us time. So if time is missing in the givens, this would be the equation to choose. And similarly, you can do that with the other parts of the grid as well. All right, let's give a problem a try. So let's say we have a driver that slams on the brakes and skids for 2 seconds before coming to a stop. You measure the skid, and it shows that the skid mark happened over 7 meters. How fast, or what is the initial speed of the car at the beginning of that slide? So what we're assuming here is that there was uniform slowing down or uniform acceleration happening during the entire time. Before that, it could have been going at a constant speed or whatever, but we're talking about at the instant they hit the brakes. So we start the timer when they hit the brakes 2 seconds after we measure the distance. Knowing the time, knowing the distance, and knowing the final velocity is 0. Why is it 0? Because they came to a stop. So there's a lot of things to read into these questions, and I want you to make sure you get that practice as you're going through it. Now, I can use any of the kinematic equations that include acceleration and these variables. I'm going to choose this one right here. Plugging in the values, I'm going to end up with about a total initial velocity of about 7 meters per second. All right, now what the idea here is take your time, solve through, make sure you understand how the problem is set up, what it's asking, and what might be some of the values that are a little more hidden. Like when it says comes to a stop, that usually means the velocity is 0. In this next section, I'm going to combine the ideas of equations with acceleration with a very common scenario where objects are accelerated, and that happens during free fall. Now, what free fall is when gravity is the only force acting on an object. So imagine that you're in an ideal place where there's no air resistance and you drop an object off of a roof of the school. That object will fall and will accelerate, and it undergoes something called free fall because it's not impacted by any other forces other than gravity. So there's no air resistance in that scenario. That makes it a very pure form of acceleration, and it's a uniform acceleration, so we can use our equations that we just talked about. So a few baseline things about free fall and acceleration. On Earth, the acceleration rate due to gravity is 9.8 meters per second every second, or 9.8 meters per second squared. That is true uniformly. That is, when objects are close to the surface of the Earth, that is the rate that they will accelerate at. I put a negative here because the direction makes a difference in these calculations. We are going to, by convention, say that down is negative and up is positive. Therefore, this tells me that the acceleration is directed downward because it has a negative sign in front of it. So the direction of acceleration, and acceleration is a vector, it has both magnitude and direction. In this case, the direction is downward. In these examples, I'm just going to talk about setting up the problem, and these are similar to problems that you'll be going over. If you drop something, know in that setup that the initial velocity is 0. You might be asked to solve for final velocity, you might be asked to solve for time, or how far did it fall. All those things you can do from this initial setup using the other kinematic equations and at least one other variable that the problem would give you. So be looking out for that. But another important setup is to remember to put the negative sign in front of the acceleration of gravity. Negative 9.8 meters per second squared. Now, it's okay. Some worksheets and sometimes I'll have you round to negative 10. That's okay. But to be as accurate as possible, we would use negative 9.8 meters per second as that acceleration value. Another setup question that often comes up is, what if you want to know the height or the time it takes to get to the top of an arc? So if a ball is thrown up in the air, it's going to go up and come back down, obviously. Well, while it's going up, the downward acceleration of gravity is slowing it down, and then it changes direction, and then it speeds back up on its way down. At the very top, the velocity is 0 meters per second. The acceleration actually remains constant and uniform for the whole path. Please separate in your mind the idea of velocity and acceleration. They are not the same. The acceleration is the rate that the velocity changes. Close to Earth, that rate does not change. It's a constant, uniform, negative 9.8. But it can change an object's velocity and will do so through the whole path. So those two are different things. It's okay to have a 0 velocity at the top and still be accelerating, because right before it got to 0 and right after, there is a velocity. Okay, I want to make a prediction. If I'm going to throw something down, so the ball will be thrown down, of course gravity is still going to act on it, but ask yourself, what other variable will change? Hopefully you answered the initial velocity. So this will have some kind of value. So VI might be like a negative 2 meters per second. I put a negative sign in there because the velocity is directed downwards. its arrow is pointing down in the same direction as the negative 9.8, or the same direction as the acceleration of gravity. So that sign is important, especially when we start to plug these numbers into our equations. All right, here's a question that puts a lot of these ideas together. You're on top of the Empire State Building and a marble drops off, and it's going to drop the full distance, 380 meters, right down to the ground. How fast will it be going once it reaches the ground, assuming no air resistance? So this is a free fall problem. All right, I'm going to look at the information they give, and so I know that the initial velocity at the top is 0. I know the acceleration is negative 9.8 because we're on Earth, and it tells me how far it travels. Notice I put negative here because it's going downwards. The direction matters. Now, I'm going to review the equations, and the one I'm going to pick is this one. I don't know the time, so this is my best option if I don't know the time. So I'm going to substitute in the things I know and solve for final velocity. All right, the initial velocity is 0, so that's fine. I can substitute that in. And then I'm going to substitute in my other values. Being careful, especially in this one, with the signs. Now, I know I can't take a square root of a negative number, but careful with what happens. The negative 9.8 times the negative 380 will make a positive. Therefore, my answer turns out to be positive as well. And I end up with about negative 86.3 meters per second. I put a negative on that because it is going downwards. So I'm going to add that at the end, even though the calculator won't say that. I'm going to add that at the end because I know it's moving down. So these are a lot of the thinkings that you're going to want to do as you are approaching the problems. Make sure you start at the basics, go back to the equations, and then think about your sign. What direction does that value have? One last question, and then I'm going to have you guys move on with the lessons. This is a very similar setup. We don't know the time, but we do know that the basketball, as it's going up in the air, is going to be experiencing free fall. So we want to know what the vertical velocity is as it required to reach the rim of a basketball hoop that is 3 meters high. So imagine you're standing under the hoop, throwing it straight up in the air, and as soon as it leaves your hands, the only force that acts on it is gravity, not considering air resistance. So a free fall problem. I'm going to look at my equations that I can use. I don't have time, so that limits me a little bit. I'm going to be using this equation again. Vf squared equals Vi squared plus 2AD. However, this time I want to solve for initial velocity, so I'm going to rearrange that equation to solve for initial velocity. Substituting in my numbers, I'm going to then do the math, and I should end up with about 7.7 meters per second. Double check your work on this. Please reach out if you have any questions. Thanks, and have a great day.